Alright, so in this video I'm gonna be explaining another important article with the title Directional Graph Networks. This paper in 2021. The lack of anisotropic kernels in graph neural networks strongly limits their expressiveness, contributing to well-known issues such as oversmoothing. To overcome this limitation, we propose the first globally consistent anisotropic kernels for GNNs, allowing for graph convolutions that are defined according to topologically derived directional flows. First, by defining a vector field in the graph, we develop a method of applying directional derivatives and smoothing by projecting node-specific messages into the field. Then we propose the use of Laplacian eigenvectors as such vector field. We show that the method generalizes CNN on an n-dimensional grid and is provably more discriminative than standard GNNs regarding 1WL tests. You see the overview of steps required to aggregate messages in the direction of eigenvectors. First, we have a graph, then we compute the first k eigenvectors. Of course, this step is for big graphs computationally expensive. So this is cons of this article. Compute the gradient. The gradient of phi is a function of edges. So that is a standard. Then to create the aggregation matrices. So we create these aggregation matrices. This is the pre-computed steps and has order of KE complexity. But for graph neural networks, once we have done this processing, then we can have a graph with node features, and X0 is feature matrix of the graph. So the aggregation matrices, these B, are taken from the pre-computed steps here. Then we have feature aggregation. The aggregation matrices are used to aggregate the features via the matrix product predict, the Bx. For B, we take the absolute value due to the sign ambiguity of phi. And finally, this MLP, this is the only step with learned parameters. Based on the GCN, each aggregation is followed by a multi-layer perceptron on all features. So the lack of directions strongly limits the discriminative abilities of GNNs to understand local structures and simple feature transformation. Most GNNs are invariant to the permutation of neighbors' features, so the nodes receive the signal is not influenced by swapping the features of two neighbors. Therefore, several layers in a deep network will be employed to understand these simple changes instead of being used for higher level features, leading to problematic phenomena such as oversquashing. So these are possible directional flows in different types of graphs. The node coloring is a potential map, and the edges represent the gradient of the potential from the arrows in the direction of the flow. The first three columns present the arcs cosine of the normalized eigenvectors as node coloring. So using directions in a graph is novel and not intuitive. So our first step is to define a simple method where we use a vector field to define a directional flow at each node. To make use of vector fields over a graph, we define aggregation matrices that can either smooth the signal or compute its derivative. according to the direction specified by the vector field. We show that using the gradient of low-frequency eigenvectors of the graph Laplacian generates interpretable vector fields that counteract the oversmoothing problem. So we present ideas of differential geometry, like think of E as these edges. You can think of it as a tangent space to the vertices. And then define the pointwise scalar product, taking two vector fields F and H, for example, and then returning this inner product. So we define the gradient as a mapping. So thus leading to analog of the directional derivative in differential geometry. So the directional derivative of function x on graph in the direction of vector field, where each vector is of unit norm, is this. Then they talk about directional average matrix, B, which is a weighted aggregation matrix such that all weights are positives and all rows have an L1 norm equal to 1. The operation is the directional average of x in the sense that y is the mean of x, weighted by the direction and amplitude of f. Then they define the directional derivative matrix B sub dx. So this is an illustration of how directional aggregation works at a node with arrows representing the direction and intensity of the field. Oh, this is important. Consider the transition W. Its entries can be used to define a random walk, a probability of move from node x to fy equal to 1 over degree of x. Notice that the probability to transition from x to y in k steps is given by x and y, by the matrix. These are the powers of your transition matrix, and this is a it's one of the specific cases of diffusion kernel, graph diffusion kernel, of course, where your coefficients are based on the heat kernel. Of course, I've seen some papers that they even learn T. So they see T as a latent variable and they learn it. And so this is, everybody knows about this. So this transition probability is also called continuous time heat kernel, as I said, because it satisfies the continuous time heat equation. Just because of this, nothing more magically defined or anything else. The diffusion distance at time t between the nodes x and y can now be written like this. Do you know why we are using this? Because if you use the conventional W, it is just related to one hop, so we cannot discover higher, more global aspects of the topology, like for example a random walk of step k, which can discover many interesting structures. So that's why they shifted to this kind of Q. And by the way, this p sub k is just the power of k, as I said. I thought they have some typo error here. Because the diffusion, should be like this, theta I a to the I. So the power of adjacency matrices times the coefficient. So this coefficient sometimes can be what do you call it, geometric distribution, sometimes heat kernel, so there are many cases, so each one is a special case for different theta. So you got that. Now, suppose the two neighboring nodes x and z are such that phi of z minus phi of x is maximal among neighbors. Then we will say z is obtained from x by taking a step in the direction of gradient of phi. And let x and y be nodes such that phi1 is less than phi1 of y, and x prime be the node obtained from x by taking one step in the direction of the derivative. Then there is a constant c such that for all c less than t, we have this diffusion distance between x prime and y is bounded by diffusion distance at time t between node x and y, with the reduction in distance proportional to e to the minus lambda 1. So this is the realization of radius 1 convolution using the proposed aggregators. I sub x here is the input feature map. The convolutional operator I sub y, Iy is the convolution result, and bi is the b of the gradient of phi. Extending the radius of aggregation kernel. Having aggregation kernels for neighbors of distance 2 or 3 is important to improve expressiveness of GNNs, their ability to understand patterns, and to reduce the number of layers required. However, lack of directions in GNNs strongly limits the radius of kernels, since given a graph of regular degree d, a mean sum or sum aggregation at a radius r will result in a heavy over-squashing of order of d to the r messages. So we can enumerate different paths, thus assigning a different weight for different r distance neighbors. So for the empirical experiments, we inserted our proposed aggregation methods in two different types of message passing architecture used in literature. A simple convolution architecture similar to one present in GCN, and a more complex and general one typical of message passing neural networks, with or without edge features. So this is optional, with or without edge features. And the degree scalar is applied to the results of each aggregator, and the results are concatenated. So they use different types of aggregators, and the effect of that, so the test set results using a parameter budget of 100K with the same hyperparameters, and the low frequency Laplacian eigenvectors are used to define the directions, except for CFAR 10 that uses the coordinates of the image.